So this is my least favorite math term. Whoever came up with whoever decided to call this an imaginary number, I wish I could go back in time and give them a piece of my mind, because what they didn't realize is that at some point we're going to have to stand in front of some high school students and say, hey, we're going to learn about imaginary numbers today. And it's kind of like, oh, what's the point of that if they're imaginary? We're going to learn about like elves and unicorns next. And I get that, right? It makes it seem like a fake or a made up thing, but the reality is it's a super useful concept. Comes up all the time in science and engineering. Anybody in here going into electrical or mechanical engineering? Like every advanced problem you're going to do, you're going to be using the imaginary number. They actually use J in engineering applications. I'm not too sure why. Instead of I, they use J. But the definition of the imaginary unit or the imaginary number I is it's the square root of -1. So you guys, spent 2 years of your high school math career being told that you're not allowed to take the square root of a negative number, and then we drop this on you and somebody gives it a ridiculous name. So my apologies to you for that. But it is a real thing. So when we talk about complex numbers, these are just numbers that contain an imaginary part. So so this is called the standard form of a complex number. We always want to kind of have it split up so that you have a real number and then another real number that's multiplied by I. Have you guys seen this notation before? This little, it kind of looks like a curvy E. It's the Greek letter epsilon, and it means belongs to or is a part of. So I have abbreviated in high-level math speak here that A and B belong to the set of all real numbers. That's what that means. Those of you who go on to advanced math classes, when you get into abstract algebra and there's like no numbers in the problems anymore, you'll be super happy that we have all of these abbreviations for things, because it keeps you from having to write out a bunch of words every time you do a problem. All right. So far, so good. Seem pretty familiar. Abstract algebra. It's cool. Yeah. It's pretty neat. I've got a book in my cupboard if anybody's interested. Seriously, there are not too many numbers in that book. All right. Let's take the square root of -121. So if it was just 121, your answer would be 11. But this is actually the square root of -1 times 121. All right. So the square root of the -1 part is the I. And the square root of 121 is 11. So we would write that as 11I. Typically, we'll put the number before the I. All right, so when we're doing these types of problems, I like to just kind of break things down into things I know the square root of. So -18, that's -1. I know the square root of that. Give me another number that goes into 18. I know the square root of 9. -1 times 9 times, if I'm trying to get 18, I need a 2 in there also. All right, so the square root of 9 is 3. The square root of 2 is I don't know. And the square root of -1 is I. So 3 root 2I. Yeah, so a lot of times these actually will have the I before the radical. I'm not going to get too picky about that, where the I comes. Same thing. Yeah, you're gonna have to be careful about making sure that the I doesn't look like it's inside of the radical. That's a great point. Thank you. This one, I don't know any things that go into 13, so it's just yeah, I radical 13 or root 13 with an I after it. All right, this is all coming back from algebra 2. Nice. Did you guys moan and groan when they told you about this whole I thing last year? Does it, let me ask you guys a question. Does it offend you how, so like in math, we kind of hide things from you when we're introducing them, like, and like it's for your own good, right? But yeah, like we tell you you're not allowed to, we tell you you're not allowed to take the square root of a negative number, and then we're like, oh, actually you can. Like, what are you going to learn about next year? You can't divide by 0, but you kind of can in calculus. Like, you'll learn about that, kind of. Yeah, not really, but kind of. Um, but it's part of education, right? We can't dump all this stuff on. As a freshman, when you're just learning how to, like, what a square root is, we don't want to be introducing the imaginary numbers. So, anyways, yeah, that's just how it goes. It's not that we're lying to you. We're just hiding some complications for a later time when you're ready, more ready for it. Okay, adding and subtracting here. This is just like combining like terms, right? You guys would have no trouble doing this if this I were an X. You would just combine like terms and put it together. So I wouldn't normally show this kind of work on this, but you are going to combine the 5 and the -3 together to get, what is that, 2? And then you're going to combine the -2i and the -8i together to get -10i, and then you'll put those together into your answer, and that's it. Bless you. You're going to have some of these in your assignment. You don't need to show me work for these. You should write down the original problem and your answer, but I don't need to see work. If it helps you, by all means, do that. Right? Subtraction is slightly more complicated because what do you got to do with this negative sign? Distribute it into the thing after it. So this is really 5 minus 2i plus 3 and plus 8i. And then just combine like terms for your final answer. So that's 8, -2 and 8 is 6i. Okay. Now, when we're writing answers like this in standard form, I do want you to write your answers in standard form, which means that the imaginary part should come at the end, the real part at the beginning. Okay. I told you I wasn't too picky about, like, in a single number, whether the I came at the end or in the middle, or, but when we're writing our answers, I do want them in standard form. All right. How about multiplying? We feeling good about those? Let's try it. So the first two here are pretty simple distribution. This first one, we're going to multiply that 6. I just realized I need to slow down because you guys don't have this sheet in front of you. I'm sorry. I will just give me the universal, like, slow down sign if I'm going too fast. Thank you, guys. All right, this is a key question. So what happens when you multiply two i's together? They don't cancel out. What do they turn into? They turn into -1. Yeah, they turn into -1. So they don't go away. The i's disappear. It's not imaginary anymore, but it does turn into a -1. So that's kind of the key thing to know as you're doing these. All right, let me get after this here. 6 times -3 is -18. 4 times 6 is 24. Got an I. That one was pretty straightforward. And the next one, we're going to have to multiply some i's times some i's. And that's the important thing, is to remember that I squared is -1. When I do these are the type of things, folks, we all know that we make mistakes with positives and negatives, right? So if I'm dealing with stuff with i's, where sometimes I'm going to end up with an extra negative on top of it, I always show maybe 1 or 2 more steps than I would normally. So I'll show you. I would do this definitely in 2 steps if I were doing it. I would write it as -2i and then -14i squared. And then I would deal with that -1 after the fact. If I try and do it all at once, half the time I'm gonna make a mistake with the negative. So I'm gonna actually do this in 3 steps. That's -2i times, and then -14 times -1. And then I would rearrange it because we want that. That's gonna end up being a +14. Let's put the 2i at the end. All right, lots of different ways to do this last one. You could use FOIL, you could use the little rainbow distribution thing. I like the little rectangle box. Rainbow distribution. I don't know what the name for this is. I think this is Mr. Skaggs likes this way, I think. That thing where you like distribute the first term, you distribute the second term. These are all just different versions of the same idea. I like the rectangle. It keeps me organized. So that's how I'm going to do it. But you do you. And then negative 3i squared. And I'll always write it as I squared. I'm not going to try and deal with negatives and negatives all at the same time in my head. That's negative 3 times negative 1, which is 3. All right, so we're about halfway through our notes for today. You guys are doing great. So something I'm hopeful that you learned last year about fractions, and this is not like a mathematical thing so much as a convention thing. There are certain things that we do not put in the denominators of fractions. Like 0 is one of them, but like what types of numbers do we want to leave out of denominators? We don't want radicals. Okay, so I was hoping that I would hear that. You guys all learned last year we don't put radicals in the denominator. And you learned some fancy ways to deal with that, mostly involving multiplying the fraction by some fancy version of 1 to make the radicals go away, right? So the other thing that we're not allowed to have in denominators is I. We can't have I in the bottom of a fraction. It really is just a simplification of a radical or a shortcut, a symbol for a radical. So we do this, we get rid of i's in a denominator by using complex conjugates. So there are some other uses for complex conjugates also. But the idea is a complex conjugate looks exactly like its complex pair, conjugate pair, except the imaginary part has the sign flipped. So a plus bi is a conjugate with a minus bi. 2 plus 5i would be conjugate with 2 minus 5i. Negative 3 minus 2i would be the same, would be the conjugate of negative 3 plus 2i. And I almost said they're the same. These are not the same. This is a different number. But there's a relation between them, and the relation is that there's a shortcut, and hopefully this shortcut is making you think of another shortcut we've talked about earlier in here. Hang on a second. There's a question. Is there any way to know it's a conjugate without context? How do you mean? So I'm not sure if I'm answering your question, but every complex number has a conjugate. Every complex number has a conjugate. So I guess any complex number is technically a conjugate of something else that's out there. The question is, like, is that conjugate useful to you or not? And when they're going to be useful to us is when we need to get rid of an I. It turns out when you multiply two complex conjugates together, your answer will not have an I in it anymore. You're always going to get a real answer. And the shortcut is you just square both things, and it's a plus in between it this time. Why is it a plus this time instead of a minus? Because the I squared is going to change that minus into a plus. Yeah, you guys are making connections. Good for you. That's fantastic. So once you know the shortcut, then it makes things pretty easy. Like 2 plus 5i times 2 minus 5i. Oh, those are complex conjugates. So I'll just square the 2 and square the 5 and add them together, and that's my answer. There's no I in it. It'd be 29. Right. So what we're gonna end up using fancy versions of 1 again. Yeah. We'll use fancy ones. All right. So here I'm gonna square my -3, and I'm gonna square my 2, and we'll add those together, and we'll get an answer. And I believe that is what, 13. 9 plus 4. Yeah. So this is going to be useful to us when we get to some problems and we've got an answer that is not in a correct form because it has imaginary numbers in a denominator. So we'll do a couple of examples here. So this is just a number. It's a complex number, but it's got problems. First of all, it's not in standard form of a complex number. Second of all, it's got an I in the denominator, and we don't like imaginary numbers in our denominator. So that's okay. We're going to fix it. I'm going to rewrite it here. I wouldn't normally rewrite it, but this is our notes. I'm going to rewrite it, and then I'm going to multiply it by some fancy version of 1. We've used fancy versions of 1. We know that we just need the same thing in the numerator and denominator. And we also know that this 2 minus I could be turned into something without any i's as long as I multiply it by its conjugates. So let's do that. Let's multiply by 2 plus I in both the numerator and the denominator. So I'm changing the way it looks, but I'm not changing the value. I'm multiplying it times 1. So on the top, we're going to have 8 plus 4i. And on the bottom, we'll square what's in front of this I. There's a 1 in front of there. We'll square the 2, we'll square the 1, we'll add them together. What is that on the bottom? That's a 5, isn't it? 4 plus 1. So my final answer, if I'm trying to put this into standard form, it does need to be split up into 2 fractions with the I part at the end. Say that again. That's a great question. So I guess I could leave the I in the numerator, and I have seen it in that format before. Our textbook is always going to have the I kind of separate with with the fraction next to it. But we could put the I up there with the 4. It would be the same thing. I'd be fine with that. Yep. Make sure it's at the end, right? You don't want to put the 8/5 at the end. And again, it wouldn't make a difference numerically. It's just convention. Someone decided that's how we were going to do it, so that's how we'll do it. All right, let's try the second one. So 3 plus I over 1 minus 2i. So that's exactly the same, and then I'm going to keep it the same by multiplying it by 1. Multiplying by 1 shouldn't change anything. What fancy version of 1 do I want? Well, it'd be nice if I could multiply this by its complex conjugate, so let's do that. Ooh, we're gonna have to do a little bit of FOIL action here. Squared, which is really just -2. I made a mistake here, didn't I? That's not 4 squared, it's 2 squared. Whoopsie. So I think we got 5 for the denominator again. So 1/5 and 7/5 I. All right. So the only other thing that I have for the notes is the quadratic equations and solving with the quadratic formula. The only difference is now we're going to sometimes end up with i's in our answer. We haven't seen that yet this year with the quadratic formula, but going forward, that's fair game. It doesn't really add anything extra in terms of difficulty. It's just like you're going to end up with a negative under that radical, so you'll pull it out and make it an I. Textbooks really stress this discriminant thing. You guys remember learning about the discriminant last year? B squared minus 4ac. And like the discriminant tells you whether your quadratic equation is going to have one answer or two answers or two imaginary or two complex answers, two real answers. I don't know why it's kind of that big of a deal because it's just the stuff that's inside of the square root, right? So it makes sense. Like if this is negative, are you going to get real answers or imaginary answers? Imaginary. You have to if it's because this is going to go underneath the square root, right? So you'd end up with two complex. If this is positive, then you've got a positive number under your square root, so then you're going to get real answers. And if this is 0, you're going to end up with plus or minus the square root of 0, which means you're really only going to get one answer. It doesn't matter if you do plus or minus. So I have not run into a situation where this was super useful to me yet. So I don't know. There's some great text in your book about it if you want to read more about it, but I'm just going to leave it at that. Let's do this thing and let's practice divide and conquer here. Set up your quadratic formula before you put any numbers in there. Set it up, make sure you got everything ready to go, and then once you're convinced that your format's correct, then go back and fill in the numbers. Takes me a couple extra seconds, but it's worth it in the long run when I don't make a mistake every 5th time I try and do this. Or minus 24 is negative 20. The other big piece of advice I would give you is once you get it to this point, go ahead and split it up into 2 fractions. All right, square root of 20. That's -1 times 4 times 5. Don't just copy my steps. Make sure you're trying this on your own and look up here if you need to check or you need a hint. The I is going to come after the plus or minus. It belongs with this part of the thing, so it needs to stay with that. Those 2's are going to cancel, so. All right. So why do you suppose we're spending most of a class period going over complex numbers? Where does this fit into polynomials? So we're going to have the imaginary zeros. Did you guys deal with imaginary zeros last year at all? A little bit? Okay, so now is this going to, guys, stick with me for just a couple more seconds. Is this going to drastically change what we did on Wednesday? Much? Not really. the biggest thing that's going to change is if this was a zero of a polynomial, we wouldn't see intercepts. You can't see these imaginary numbers on an XY graph, right? So if there were imaginary zeros, then we're not actually going to see them as intercepts. But that's actually kind of good, because that's less of those kind of in-betweener points that we got to test with the P over Q. These actually end up going a little bit faster when there's imaginary zeros. What do the imaginary zeros do to equation on a graph? Does anybody know the answer to that? They make it more wiggle. Yeah, more wiggles. Yeah. 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 Shh. Hey guys, quiet, please. Over here. So what I like to do, and I usually won't. I've done this enough that I can usually do it in my head, but I think of negative 20 as, first of all, the negative. That's the I part. And then I think of the 20 as 4 times 5, because I know the square root of 4 is 2. And I don't know the square root of 5, so that has to live inside. So I'm kind of showing my thought process here. Negative 20 is negative 1 times 4 times 5. Square root of negative 1 is I. Square root of 4 is 2. And the square root of 5, I don't know, so we're going to have to leave it in there. Yeah, absolutely. Thanks for the question. Any other questions? All right, folks. That gives us a decent chunk of time to start on our assignments. For those who had questions about 49, 50, and 51, I'd be happy to address those at this point.